Good morning, everybody. Hopefully you can hear me okay. I'm Brad Jolliffe. I'll be introducing our speaker this morning. Welcome to Saturday Science. This is number 5 of 6 Saturday Science episodes that we're bringing this semester from the McDonnell Center for the Space Sciences here at Washington University. Absolutely delighted to introduce this morning's speaker, Dr. Scott Van Bummel. Scott is a senior research scientist at Washington University in the Department of Earth and Planetary Sciences. Scott has been involved in Mars rover missions going back to the Mars exploration rovers, which is where I first met Scott. And he is now involved in activities with both of the big rovers, Perseverance and Curiosity. It's absolutely a real pleasure to be introducing Scott. Before I introduce his title, let me just remind everybody, Zoom etiquette, y'all are very good, and I know you're used to this. Please try to keep your microphones muted during the presentation. Apologies for the background noises.
Thank you.
And if you have any questions, please put them into the chat and we'll be sure to get to them at the end of the talk. So let me go ahead and introduce Scott. As I say, I got to know him when we were working together on Mars exploration rovers. He worked with the APXS instrument, which is, he'll probably tell you about that. It's an instrument that determines chemistry, and it's absolutely phenomenal what we've been able to do with Mars exploration. But I want to say that my first presentation on Mars sample return goes back about 20 years. And so this is a topic that's very near and dear to me. And I think you'll be very interested to hear what Scott has to say about Mars exploration with rovers and also this business of sample return. So title of Scott's presentation is Towards the Science Gold at the End of a Mars Exploration Rainbow, Mars Sample Return. Scott, why don't you go ahead and take it away?
Thanks, Brad. And so today we are going to be talking a little bit about rovers on the surface of Mars and really the evolution of exploring Mars, why we are exploring Mars, and the various stepping stones that we've made technologically and scientifically in an effort to bring back a well-characterized cache of samples from the surface of another planet. And I'll be approaching this presentation with kind of a perspective and a lens from a science team member on now 3 rovers that have operated on the surface. So let me see if I can change slides. There we go. All right, so we'll start by a very brief overview on Mars. Then we'll talk about past, active, and future missions before discussing what it's actually like to operate a rover on Mars. This is not something that you encounter every day, and there are some challenges that arise just simply because you are operating a spacecraft on the surface of another planet. And then I will do my best to summarize some of the significant discoveries that these missions have made. It's far too short of talk to give a really comprehensive summary, but I'll just touch on the high-level topics there before moving into the importance of Mars sample return and why this is something that we've been pushing for a long time. As Brad had noted, he first gave a talk on Mars sample return 20 years ago. So it has been a long and lengthy process, but we can see the light at the end of the tunnel. And then we'll wrap with talking about the impact and implications of this work and why all of this is really important and what it kind of gives back to society. So first, let's talk a little bit about Mars. So as we all know, Mars is our red neighbor in the sky, and it's quite different from Earth if you were to look at it now. But I'm hoping by the end of the talk, I'll have convinced you that this was not always the case. And even though Mars is a little bit smaller and it doesn't have quite the striking colors and contrast that Earth does, it does still have some really interesting geography and geology especially. So in the picture there, you can see Mars is roughly half as big as Earth, but right front and center of that image is Valles Marineris, which happens to be the largest canyon in the solar system. And if you were to look at Mars more closely, you'd also find that it has the largest mountain in the solar system, Olympus Mons, and you can see an image there comparing it to what are the tallest mountains here on Earth. And also, you probably know that Mars is a very cold and hostile planet. So its atmosphere is roughly 95% carbon dioxide, and the combination of the low pressure and very cold temperatures actually results in the atmosphere freezing out at the winter poles. And you combine this dry ice, this frozen CO2 with some water ice, and you get these really striking white polar caps at each end of the planet, particularly the winter pole. But if we want to talk about Mars, we can go back even further to Schiaparelli in 1877, who had made some observations of Mars from Earth and had noted that there were various canali, which are grooves or marks across the surface. And the media totally mistranslated this, and it went the equivalent of 1800s viral with canals and rumors of life. And you can see in the one paper article there, Martians build 2 immense canals in 2 years. You can imagine why this would be a little concerning when you have, potential for alien life forms in a neighboring planet that can not only pass infrastructure legislation, but build something in just a couple of years. So we know that this was not the case, but a little mistranslation and the equivalent of 1800s viral, and there's a little bit of hysteria. But thankfully, we've made some progress over the years. This represents the first image we have of Mars from near Mars. I use image in air quotes because what this actually represents is the Mariner 4 spacecraft did a flyby of Mars and took a series of images, and the scientists on that team could not wait for the computer to process that image. So what they did is they printed out the data and did kind of a color by numbers after running to an art store nearby and grabbing some pastels. So this is kind of our first air quotes image that we have of Mars. And since then, we have made significant leaps and bounds forward in our capabilities. So on the right of this slide here, you can see a high-rise image taken of Jezero crater. So this is an impact structure on Mars. There was past water activity here. As you can see, there's a kind of a canal or valley through the rim of the crater there. And much like the image on the left, where you have river delta in Alaska, you can see the same kind of structure here, where you can draw the parallel that there was water flowing into this crater, and as the moving water hit the standing water and began to slow, its ability to carry sediment decreased, and it began depositing that sediment kind of at the river mouth where it hit the Jezero crater lake. So this capability of really high resolution images, as well as orbital spectral data, has been enabling for the surface missions, and we'll touch more on that later. So Mars today, again, we see these striking polar caps, and it looks very different from Earth, but through the rest of this talk and in the motivation towards Mars sample return, I hope that you'll be convinced that Mars was not always as it is today, but was once much warmer and wetter. So with that, we will transition into past, active, and potential future missions. And really, the surface of Mars has been explored primarily by NASA-led missions. The first vehicle to successfully land on Mars and transmit data was actually from the Russians. But by and large, it has been an American-led effort. And for the purpose of this talk, we'll be focusing on Spirit and Opportunity, as well as Curiosity and Perseverance. And as far as active rovers go, we have Curiosity, Perseverance, as well as a Chinese mission that landed during this past launch window. And then we also have the InSight lander, which is not a rover, it's a fixed position spacecraft that is still operational. So I mentioned the Mariner 4 mission in the mid-1960s. The first artificial satellite of Mars was actually Mariner 9. So this was the first spacecraft that was put into orbit around Mars. And shortly thereafter, the Soviet Union landed the Mars 3 Prop M rover. It's the image in the center there that kind of looks like a kid's toy out of a Happy Meal or something. But they had the miraculous misfortune of performing a landing on Mars during a global dust storm. So whether or not that played into the tiny rover's ultimate demise 20 seconds after landing. We don't know for sure, but it did transmit a partial image from the surface during those 20 seconds. And then in the mid-70s, we had the first sustained surface operations of spacecraft with the Viking 1 and 2 landers. Again, these are fixed position spacecraft, but they were equipped with a really remarkable scientific payload for that time, and their data are still used today and contribute to our understanding, or you could say some of the debate as to much of the science and what we know about Mars. And then there were the 1980s, where this is not a glitch on your screen. We didn't really have much in the way of successful missions to the surface of Mars. But that all changed and really started with the first Mars rover, and that was Sojourner, which flew on the Mars Pathfinder mission and landed in 1997. And what's particularly important about this mission is not only does it represent the first kind of mobile science platform on the surface of Mars, it also contained an alpha proton X-ray spectrometer. This is an instrument that can tell us the composition of materials, and it was located at the front of the rover, kind of like a bumper in a way. And you can see the rover there has driven up to a rock. It has placed the alpha proton X-ray spectrometer into close proximity with that rock. And this really represented our first real measurement of rocks on Mars, where the Viking mission had primarily been able to focus on the sand, soil, and regolith around the spacecraft. And then in 2004, we had twin rovers, Spirit and Opportunity. They landed on opposite sides of the planet, and they took an additional leap forward where Sojourner essentially couldn't venture too far from its landing platform for various reasons, whereas Opportunity and Spirit had all the hardware it needed for communications and everything like that on board, and were able to conduct extensive traverses and really explore their respective landing sites. And then in the late 2000s, we had the Phoenix lander. This was a fixed position spacecraft that landed above the northern Martian Arctic Circle, and was looking at frost and potential near subsurface ice and things like that. And then active missions that we will not be really discussing in detail today. There's the InSight lander. This is a spacecraft that is focusing on trying to better understand the Martian interior. As you can see, it is very dusty right now, but still operational. And then we have the Chinese mission that landed a rover in May of this year. And the picture there you can see is actually taken by a single-use camera that the rover dropped in front of it and backed up for this selfie. But as far as active missions, that will be the focus of this talk. Those include Curiosity, which landed in 2012 in Gale crater, and also Perseverance, which landed this past February in Jezero crater. And I'm incredibly fortunate to be working on both of these missions. So with that, let's dive in a little bit deeper into the focal missions of this presentation today. So Spirit landed in Gusev crater just a few weeks ahead of its twin Opportunity. And Spirit was really the tough luck, work hard rover. So it landed in Gusev crater and made its way to the surrounding hills and really did some fantastic science that we'll touch on in a little bit. But I wanted to include a couple images here, not only the landing site, but at the bottom you can see a panorama. And in that panorama, you can see within the tracks there some scuff marks, and those come into play later as well. But also the iconic image, my personal favorite image from this mission is in the top right there, where you have it capturing a sunset with the gorgeous blue sunset there. And then Opportunity landed in Meridiani Planum, specifically Eagle crater. And part of the reason why it was called Eagle crater is because the final sequence of when it landing on the surface, the rover is essentially wrapped in an inflatable bouncy ball. So it bounces around on the surface until eventually coming to a rest. The bag deflates and the landing platform opens and the rover drives off. Now you can imagine launching from Earth, landing on Mars in this tiny little impact crater is kind of analogous to a multi-million mile hole-in-one. So that was part of the reason why the name Eagle crater was chosen. But you can see there as well, there's a lot of rover tracks kind of right at the rim of that crater there, where there's some bedrock exposed, or a little bit of an outcrop. And this will feature later on in the presentation as well. But eventually Opportunity made its way out of Eagle Crater and traversed all the way to Marathon Valley and beyond. And Marathon Valley there, you can see at the bottom, this is a mosaic. And this is where Opportunity shattered the marathon distance. That's the longest distance ever driven by a spacecraft. So the longest distance ever driven beyond the surface of Earth, even more so than the Apollo moon buggies. And Opportunity conducted extensive science within Marathon Valley before moving on to another nearby valley, Perseverance Valley, where it ultimately, sadly, met its demise in 2018. But the image there that you see in the top right, this is a selfie. So there's a camera on the end of Opportunity and Spirit's arm. And to commemorate the rover's 5,000th day, so 5,000th sol actually, and the sol is a Martian day on the surface, we took a selfie of the camera, taking a series of images with the fixed focal length camera and stitched together this little mosaic. And unfortunately, 111 sols later was the last time we heard from Opportunity. But all things considered, both Spirit and Opportunity were only anticipated to survive roughly 90 days on the Martian surface, in large part due to the anticipated buildup of dust on their solar panels. But between these two missions, we got roughly 20 years combined out of them. So they're really fantastic and triumphant spacecraft. And it really is a testament to the design and engineering that went into them. Curiosity, as I mentioned, landed in 2012. It was sent to Gale Crater in large part to kind of fulfill its mission, which is to determine if Mars could have ever supported life. So Spirit and Opportunity were sent to look for signs of past water, but Curiosity is taking that a step further and is looking to determine if at some point in Martian history, conditions were right that life could have survived. And there are various reasons why Gale Crater was chosen. So Gale Crater is this roughly 150-kilometer diameter impact structure. And in the center, there's this mountain called Mount Sharp. So if you look in the lower right image there, you can kind of see around the horizon, the crater rim. In the near foreground, you see these two little blast marks where the sky crane thrusters kind of blasted away some of the surface. And you'll see a better image of that in the next slide. And then kind of right middle of the frame there, you can see Mount Sharp flanked on the near side with these dark streaks, which are these giant sand dunes. But if you get a closer look at Mount Sharp, what's really striking is you have these layers, the strata here. And when you explore this with the rover, you can drive up the side of the mountain here. And this mountain is roughly 6 or 7 kilometers tall, so it's not small by any means. And when you drive up the side of this mountain, you're essentially exploring different eras in the history of Mars. So you can kind of think of it as the rings of a tree. So we can go to one location and we can explore a vast swath of Mars's history. And Perseverance landed this past February. And I mentioned before the sky crane, and you can see it there on the right, but we got a lot of really tantalizing images from this mission, even before the wheels even really touched down on the surface and the spacecraft became fully operational. So in the top left, you can see HiRISE, again, orbiting Mars. I was able to capture an image of Perseverance coming into land. You can see its parachute deployed and the Jezero Delta right there. And then if you look in the lower right, we have a picture taken from the sky crane. So this is essentially a rocket-powered jetpack that lowers the rover onto the surface by a series of cables. And there's a camera on the top of that descent stage that captured video of the parachute deploying, which is important for understanding entry into Mars and better preparing for future missions. And it also has a camera looking down, which captured the rover deploying, and then the rover had a camera looking up, which captured the sky crane, and really just provided fantastic video of the entire landing sequence that was really unprecedented. But serendipitously, after the sky crane safely touched Perseverance down on the surface and severed those cables in the umbilical, it flies away and crashes into the surface at a safe distance where it's not going to be impeding any of the science that the mission wants to do. And just by pure luck, when the rover touched down on the surface and fired up a couple of its cameras, one of those cameras happened to be pointing in the exact direction where the descent stage crashed. And you can see in the lower left frame there, there's actually a plume of dust where this impacted the surface off near the horizon. And of course, you can't talk about Perseverance without talking about its little buddy, Ingenuity. So Ingenuity is a tiny little helicopter, primarily sent as a technology demonstration. So to better enable future potential powered flight on Mars. So it has successfully completed multiple flights now, including the first powered flight on Mars. But what we learn here, in addition to potentially enabling additional helicopters and rotorcraft to travel to Mars, we also will be using this information to not only better prepare for a particular mission, Dragonfly, which is sending a rotorcraft to Titan, but also to help scout for the rover. So this helicopter can get an advanced view of the area that we are planning to explore, and this can expedite our ability to drive and traverse, particularly terrain that is difficult to get across safely. So this is kind of, again, a very brief summary of the missions that will come into play in this presentation here. But really, as far as future exploration goes, there's not really a science-focused rover on the books right now. So Perseverance is collecting a diverse array of well-documented geologic material to eventually bring back to Earth. So it is the next step in Mars sample return. So the missions that are currently focused through the international community on Mars are primarily focused on collecting those samples, bringing them to a Mars ascent vehicle, putting the samples into orbit where it is fetched by an orbiter, and then ultimately returned to Earth for scientists around the world to study in great detail. And this all kind of feeds in as well into the Artemis program, which is a mission, or a sequence of missions rather, to achieve a sustained presence on the moon, and also use the moon as a launching pad to Mars, including potentially sometime in the distant or maybe not so distant future, humans on Mars. And of course, you can't also talk about future Mars exploration without at least mentioning potential roles that commercial providers may play. They've really pushed the boundaries of technology and space exploration lately. So it remains to be seen what role they'll play in future Mars exploration, but I'm pretty confident that it will not be zero. So with that now, let's transition a little bit into what it's like exploring with Mars rover. So this is not something that you typically encounter every day, and it's very different and kind of from what you'd expect with kind of day-to-day goings on Earth. So first and foremost, for anyone who has watched The Big Bang Theory, there are a couple things that you may recall from the show. One of which is that there was a show, an episode, or a sequence of episodes where they were controlling the Mars rover from a control room. And there are a few things that were wrong or off with this scene or sequence of scenes. For one, at least me, I don't have the bravado or confidence to pull off a Howard Waldwitz outfit like that. But also, and perhaps more importantly for this talk, there's no real one room you can go to control the rover. And more importantly, you can't just grab a computer or joystick and control the rover in real time. And there's one really important reason for that, and that is Earth and Mars are pretty far apart. We may be closest neighbors, but at our closest approach, it still takes 4 minutes for any communication from Earth to reach Mars. And likewise, it takes 4 minutes for any communication from Mars to reach Earth. And that only increases as Earth and Mars get further and further apart, all the way up to a little over 21 minutes one way at the speed of light. And in addition to that, you arrive in the situation every few years where for 3 weeks you have to stand down operations because the sun blocks your communication line of sight between Earth and Mars. So if you
Scott?
wanted to, yes.
Sorry for the interruption. There's a request that please feel free to use your pointer.
Oh, okay, I can do that.
Okay.
Sorry, I saw the chat popped up, but I didn't want to open it up in case it blocked the screen or anything. But yes, I will do that. Can you see my cursor?
Yes.
Okay, great. I will do that then. Okay, where were we? Yeah, so if you say you wanted to try and control the rover in real time, or say communicate with the rover in real time, best case scenario, you would send a command or communication, and 4 minutes later it would be received, some action would be taken on Mars, and then 4 minutes later you would receive confirmation or feedback. So it is, latency is a very real thing that occurs when we're conducting rover operations. And further to that, while we send commands directly to the rover from Earth, for various reasons, we actually relay the data from Mars through satellites orbiting Mars. So we don't communicate kind of constantly with the spacecraft in either direction. And then you have the reality that Mars is a different planet and the duration of days are different as well. So a Sol is a Martian day. It is roughly 40 minutes longer than an Earth day. And if you think about it, because we can't command the rover in real time, and it is also advantageous to acquire a lot of your images and data during the daytime where you can see the terrain around you illuminated quite well, this essentially manifests in us working the night shift on Mars. So when the rover, say Curiosity, goes to bed in Gale crater, we essentially will start assessing the data that it acquired. We will start planning what the rover is going to do, and then we will send it those commands in kind of like a sequenced bundle that the rover will then receive, and then when it wakes up, we'll execute those commands on its own. But because a Martian day is longer than an Earth day, this essentially means we are jumping time zones every day in order to kind of synchronize with the difference in day duration between Earth and Mars. Now, historically, this has typically only been done during the start of missions where we're trying to get the entire spacecraft up and running and getting early science done, because ultimately at the end of the day, living on Mars time is not really conducive to having a personal or Earth life. So after the first 2 to 3 months or so in a non-COVID year, everyone would kind of disperse back to their home institutions where we not only conduct remote operations, but our shifts are scheduled to kind of find the happy balance between Earth time and Mars time. And when we are staffing these shifts and planning what the rover is going to do, it is essentially a sequence of meetings, as I mentioned, where you are downlinking the data, assessing the science, as well as the health and safety of the spacecraft and its various payloads, and then planning what the rover is going to do and validating all the commands through a sequence of meetings throughout the day that run in parallel with other science-focused activities. And it's throughout these meetings that you are really trying to get the most out of the vehicle. So there's a significant investment, obviously, that goes into these spacecraft. So you want to get as much science return from them as you can, but you are limited by the realities of the fact a Martian day is only so long, the rover only generates so much power, and we can't just transmit every single megabyte that we want back to Earth. So the realities of time, power, and data play into what we do as far as planning on Mars, as well as the various constraints and limitations of the instruments and certain times of day and temperatures and things like that, that the rover hardware needs to operate or to achieve the scientific goals. And then there's the reality that we're operating on the surface of another planet. So if you were to be conducting many of these experiments on Earth, let's say X-ray spectroscopy, you would be doing these experiments in a very well-controlled laboratory with a sample that has been meticulously prepared, and we just don't have that luxury on Mars. So we can't target with micrometer precision. We're limited by placing X-ray spectrometer with the accuracy of a rover arm, which, mind you, is within, say, the diameter of a dime, which is fantastic if you consider, we're on another planet. There's thermal expansion and contraction due to the massive temperature swings that you experience on Mars. But the reality is, operating on another planet is not easy. Was there a question there? I thought I heard somebody. Okay. So the environment is definitely something that plays in. We have to kind of synchronize heater sequences, the favorable temperatures for various instruments, and then you also have pressure fluctuations as well that can play into some of the science. And then you have dust, and more dust everywhere. So Mars doesn't have an ocean like Earth. There's no sink for this material. Yeah. So it gets well mixed on the surface, gets lofted, floats around. You get little dust devils that whip around on the surface. And every few years, you can have a global dust storm. So this is where you have a massive storm that encompasses the whole planet and can ultimately blanket out the sky and block out the sun. And this is unfortunately what caused Opportunity's demise, where we had a massive global dust storm really centered almost right on top of the rover. And you can see in the right frame here, as I demonstrate use of my cursor, kind of what the rover saw and what we predict it saw towards the height of the dust storm as the sun just gets more and more blocked out. And you can imagine with a rover that is solar powered and needs to generate some minimal amount of power just to maintain survival temperatures, how this could be problematic. Then there's also the reality that you are isolated. There's no Martian AAA, there's no one you can call for help. So if something happens on the rover, you can't exactly just go up and fix it. You can use the rover in different ways. You can perform software updates or fixes, but the reality is, if something goes wrong, you have to get creative and you can't fix anything that physically breaks. You can mitigate the effects of it, but you can't physically correct anything on the rover, essentially once it's integrated into the launch vehicle. And in the case of Spirit, it was driving across the surface of Mars, encountered some soft material that was hidden beneath rather, a kind of crusty veneer on the surface, and it got itself into a little bit of a predicament. And unfortunately, with winter approaching and the rover in a non-optimal orientation to get sunlight during the winter, it was unable to free itself, and there was nothing that could be done ultimately to save the mission. And continuing with this theme that Mars is a tricky place to explore, Mars also is a bit of a prankster. So you can see here, we're exploring Mars through the lenses of these rovers, and there's some really puzzling things that you can encounter if you tend to look too closely at some of these images, can start to play tricks on your brain. So you can see there in the left image here, something that looks like a floating spoon. It's just a piece of rock that had differential erosion compared to the area around it. And then here you can see a rock that looks like it's floating. This is just an artifact of the lighting, and then a lower area in the rock behind this front piece here that makes it look like there's no shadow there. And then one of my favorite instances, this rock here, was encountered by Opportunity. And what happened was the rover had taken a series of images in the area around it, conducted a tank turn, and then took images again of the area around it. And between those two images, this little rock here kind of popped up and was not there in the first sequence of images. So what had happened was when the rover turned, it had dislodged a piece of rock on the surface and kicked it over here, and we just happened to take a picture of it. And not only did we get some pretty informative science out of there, looking at kind of the underside of this rock, but it actually led to NASA being sued because there was someone online who was convinced that this was a fungal spore. Obviously it was not, but it did happen. So on that similar kind of vein, all these images, everything we acquire on these spacecraft is public domain, and the images go up pretty much immediately. So you get a lot of people who look at the images and make claims like proof of life on Mars, where you see this image in the left, and it looks like you have this Celtic cross or Gaelic cross compared with Earth and Mars. But I wanted to show this because it emphasizes the importance of scale. And this here on the left, this is actually a screw from an imprint of the Mossbauer instrument. So the scale here is very different. But what's important, and something I continually have to remind myself about, is when you are exploring Mars, we don't have the luxury of having anything with relatable scale that we can tie the images we take to. So there's no trees, there are no buildings, there's nothing that we can relate to here on Earth that gives us an appreciation for the scale. So when we take these images, it's incredibly important to remember the scale, and what may look like it is a couple feet large, may only be, an inch or so. And then distances are just incredibly hard to judge without kind of computerized assistance. So scale is important. And again, exploring Mars through the lenses of these rovers presents a lot of things that can be a little bit deceptive to our Earth-trained brains. And then the reality is, exploring Mars, there are even more challenges. So you can have a reduction in scientific payload. I just mentioned the Mossbauer instrument. Here's a nice, clean, shiny version of it there. And Spirit and Opportunity both carried a Mossbauer instrument. The missions were only expected to last for 90 sols. So the instrument here utilized a radiation source to conduct its science that had a half-life of 270 days, which means after 90 sols, you'd have roughly 80% of your activity left and everything is bueno. However, at the end of the Opportunity mission, over 5,000 sols into a 90 sol mission, you have roughly 1/1,000,000th of the source activity left. And for quite a time, Mossbauer was considered kind of not operational, just even though it hardware-wise was working fine. Just the natural progression, and over time, you do have a reduction in scientific payload. There's also general wear and tear and degradation of spacecraft hardware. So in the center frame here, you can see one of Curiosity's wheels has seen better days. These holes in the middle aren't so much a concern. What we're most interested in monitoring the potential fracturing of these grousers here. And we've done significant testing to see what we can expect for the lifetime of these wheels. And as alarming as it may look, everything points to the fact that these wheels will last for the duration of the mission. And then lastly, you also have the general nature of consumables on the rover. So, you have hardware that every time you use it gets one potential iteration closer to failure. Or in the case of Perseverance, you have this little ball here and it contains compressed gas that we expel onto the surface to remove dust. And because it's non-rechargeable, essentially once that canister is empty, that capability has been removed as well. So, it's much different operating a rover on the surface of Mars, especially compared to the type of experiments and the control that you have in order to do similar science here on Earth. So with that, I want to transition into significant discoveries and keep in mind all the operational challenges that these rovers face to conduct this science. And it's incredibly difficult to summarize what will essentially be 30 or 40 years combined of Mars rover science into just a few slides. But I just wanted to touch on select key discoveries. And you can't talk about surface operations really and the science that these spacecraft collect without touching on orbital instruments and spacecraft as well. So these satellites orbiting Mars provide essential data for spacecraft operating on the surface. So we get high resolution images that help us plan our traverse across the surface. There are spectra that are required from orbit that help inform us as to where there might be evidence of past water. So on the right image here, you can see potential outlines of all these different mineral signatures that we see, and each of those has a different tie to potential past aqueous or potential past water activity. And you can see something similar here. This is obviously not real color, this is false color, but it's a similar type of approach at Jezero Crater. So these orbital data help us guide the mission when we're on the surface, but furthermore, they're really our eyes in the sky that point us into the landing site that will be most suitable for our science goals. So not just at a local scale, these orbiters are essential for helping us choose the landing site on Mars that will provide us with the best science return for our mission. So Spirit, the first of the twin rovers sent to look for past signs of water on Mars, again, landed in Gusev crater. It was really a claw for every inch kind of try hard rover. And again, hard to summarize 6 years into one slide. But the science that I think is most interesting largely came from an area around home plate. So home plate, you can see here, and this is actually a picture taken from orbit with Spirit driving around it. And it was called home plate because it kind of looks like home plate on a baseball diamond. But this area was actually determined to be a volcanoclastic feature. So you have hot volcanic rocks that come into contact with water and caused a violent eruption. And there's a lot of evidence around this area for past hydrothermal activity. So this is warm water coming from the subsurface and very likely acidic in nature. Spirit also discovered sulfur-rich material. So you saw in an earlier slide, the tire tracks on the surface kind of looked like it was gouging out some of the soil as it drove along. And that's because one or more of Spirit's wheels kind of stopped working, and in doing so was digging trenches as it was driving along the surface. And one of those trenches here unveiled this bright material within the characteristically red Martian soil. And when we analyzed this material, it was suggestive of an evaporate deposit that would only occur once if water was present. And actually, analyses of this material also showed that significant water was present in this bright material, just bounded to minerals. And then also Spirit discovered some carbonates in a rock called Comanche back in 2005. And what's important about carbonates is that they originate in wet, near neutral pH conditions, but dissolve in acidic conditions. So this is suggestive of that the water that was once here wasn't necessarily always acidic as we had seen in previous data, which pointed to more acidic conditions. So this is kind of a first indication that the environment may have been more favorable to life than these earlier data suggested. And then Opportunity, again, 10 years, one slide. Basically, everywhere it went, especially around the rim of the various craters it visited, there was extensive evidence for past water being present, including the presence of thick veins. So you can see here in the bottom here, this is a vein. Essentially, you have this mineral that is soluble in water, and as the water evaporates, it deposits this mineral within cracks within the rocks. And this here is, in particular, is calcium sulfate. It's roughly 1 to 2 centimeters wide, and this vein in particular was 40 to 50 centimeters long. And depending on the amount of water bound to the calcium sulfate, this essentially is what we make drywall out of here on Earth. So it can only form if there's water present. But really, you can't talk about the science conducted by Opportunity without mentioning the blueberries that it encountered right when it opened its rover eyes, if you will, in Eagle Crater. So just driving off the landing platform there and exploring this outcrop, the rover discovered a vast quantity of blueberries. So these obviously aren't blueberries, but they're hematite, so they're an iron-based mineral that precipitates out of water. And what I think was particularly interesting was as Opportunity left this site and began to conduct its traverse and slowly gained in elevation, these blueberries were present, but slowly began to wane in frequency and coverage. So this kind of gives us a proxy to estimate the amount of water that was present in the vast plains of Meridiani Planum. Curiosity is no stranger to encountering signs of past water on Mars. So here, this is a really striking vein network that we encountered at Garden City. So you have the white material there, which is the same calcium sulfate precipitates out of water. But then when we characterize this dark material with the APXS that I work on, we found chemical evidence that is pretty suggestive of past hydrothermal activity. So again, You have warm water coming from the subsurface, potentially acidic. And when you combine that with the fact there are calcium sulfate veins there, it's also suggestive that there were multiple episodes of water activity interacting with these materials that are now at the surface. Curiosity is also equipped with a percussion drill that can collect material from rocks that we are analyzing and provide them to instruments within the belly of the rover. And when we've conducted many of these drills, we have found minerals that are indicative of neutral pH, essentially drinkable water that was once present on the surface of Mars. We've also found organics, which I'll present briefly in the next slide within these rocks. But by and large, everywhere Curiosity has gone, we have seen an abundance of evidence for past water. Calcium sulfate veins everywhere. You also have rocks that look like this on occasion, where you have polygonal fractures, desiccation cracks. Essentially, you have a wet, say, mudstone that dries out and cracked like that. And then you also have nodular features that are suggestive of precipitation out of water as well. So by and large, when you integrate all the data that we've acquired with Curiosity so far, the leading theory right now is that Gale crater, this 150-kilometer wide impact structure, was once flush with water and potentially a crater lake. So I mentioned organics briefly. You can see here some of the organics that we found in at least one site when we drilled the rocks. Now, on Earth, obviously, we associate organics with biologic activity. However, this is not necessarily the case on Mars. There are abiotic processes by which organics can be formed, and we unfortunately don't have a way to distinguish whether these, which vector these arose by. And similarly, when we conduct measurements of the atmosphere, we detect methane. And of course, here on Earth, we associate methane with life, in particular cow burps. But on Mars, there are definitely no cows. And there are ways without life that methane can be formed. And again, we can't distinguish between biotic and abiotic processes in the production of methane. And Perseverance, just to give a very quick overview. So Perseverance is the latest rover that had landed on Mars after a characterization phase has begun driving along the surface of Mars towards the Jezero Delta and conducting science, and also importantly, acquiring cached samples along the way. So Ingenuity, as I mentioned, continues its operation, flying on Mars and also benefiting the rover in terms of scouting terrain ahead. But the rover has collected a number of samples already this far that we've thoroughly characterized. And then, as you can see, we pull a drill core from a rock, or multiple in this case. This rock's called Rochette. And then the rover automatically processes that sample, takes an image of the sample within the sample tube before it is sealed, and ultimately awaits potential selection for delivery to Earth through subsequent spacecraft. And then I just wanted to include this picture here for those who are more geologically inclined on the line. This is an abrasion patch of a rock that we just acquired. It was posted on the public image website very shortly after the data arrived on Earth. And I just wanted to show you guys kind of what it looks like, these Martian rocks up close. So this here, you can see kind of the edge of the abrasion bit here. This diameter is roughly 2 inches for a sense of scale. And typically we conduct these abrasion patches when we want to analyze in detail the inside of the rock, which is not potentially altered by exposure to the surface. And we also have a clean, flat area. So we have the kind of a true impression of what the composition is like, and can start to characterize it thoroughly for determining and potentially caching a sample from here. So this may be on the horizon, and I think the rocks that we're analyzing here are pretty striking. But unfortunately, we'll have to wait till an announcement or the science publication comes out to talk about the science in more detail here. So with that, I just wanted to kind of segue into the importance of Mars sample return. So we have these rovers operating on the surface. Why is it important for us to invest in and strive towards Mars sample return? So, each of these rovers has been a stepping stone closer and closer to bringing Martian materials to Earth. So the first thing when it comes to Mars sample return is you need to think about the hardware that we're using on Mars. So this here is the SAM instrument on Curiosity. It has multiple different experiments in here. And if you were to do these experiments in a terrestrial laboratory on Earth, they would roughly take up an entire room, and they've been shrunk down to the size of a microwave. And really, when you are building hardware and instrumentation for spaceflight, you have an incredibly tight envelope that you have to fit. Power demands, weight and size are big ones, and all of this comes with compromise. You can't take a giant instrument to Mars. It's just typically not feasible. And a good example of that is this here. This is the Chemin X-ray diffractometer. So it uses X-rays to look at the crystal structure of materials by looking how they diffract or how they scatter off of crystal structures within the atomic lattice of the materials. And on Earth, what XRD typically consists of is you have a sample cup in the middle, and then you have the source of the X-rays and the detector that kind of rotate around the sample. And it's a pretty big apparatus, and it's not really something that is conducive to flying to Mars. So instead, what they do is they deposit the sample into a cup, and then they have a mechanism very similar to what causes your cell phone to vibrate attached to each cups, and then it vibrates the sample around, so that way it kind of reorients itself and you get a vast array of different scattering angles to analyze. But again, going back to the theme that Mars is a difficult place to explore, the gravity on Mars is roughly a third that of Earth. And turns out when you run these vibrating cups, it expelled much of the material from those cups into the bottom of the instrument. So they have to employ what's called kumbaya mode, where they actually vibrate a cup next to the one that has the sample we want to analyze in, and then the kind of residual vibrations kind of lulls the sample into moving around enough that we can conduct X-ray diffractometer science on them, but not expel it from the cup. So, point of this slide is the hardware that we fly to Mars has incredible limitations in terms of size and scope. And here in the middle is the APXS on Curiosity that I work on. It is kind of, in my opinion, in my very biased opinion, a perfect instrument for flight because it's compact. It's roughly the size of a pop can, or if you want to convert that from metric to imperial, a soda can. And you have radiation sources, and it's compact, low power, low weight. But it doesn't have the same capabilities if you were to do X-ray spectroscopy in a lab. We don't have the ability to powderize samples. We don't have the ability to target to micrometer accuracy, very, very small points. So there are some limitations. And by bringing materials back to Earth, what it comes down to is we can use our full technological capabilities and achieve more science than we can using flight hardware. Further to this, Mars sample return, we have material on Earth that we know has come from Mars. So we have Martian meteorites. These are rocks from Mars that were ejected from the surface during an impact event, and while in orbit around the sun, crossed Earth's path, and just by dumb luck, didn't fall into the ocean and fell somewhere that we were able to find them. And we know they're from Mars for various reasons, including the fact that there's some gas bubbles trapped that happen to match the composition of the Martian atmosphere precisely. But the problem with these stones is that we don't know exactly where they came from. So they lack context. And this makes it difficult to try and parse together the colossal puzzle that is the history and evolution of Mars. So on top of that, you have these rocks, they're liberated from the surface during a giant impact event. There could be a lot of mixing. There's definitely a lot of alteration. You have the fusion crust from when it's plowing through Earth's atmosphere and getting very hot. And this just kind of adds to the complexity of trying to kind of understand their origin and some of the assumptions that have to be made. So what it comes down to is Mars sample return really enables us to utilize our full technological capabilities to conduct advanced studies of these materials. Terrestrial laboratories, we can have a controlled environment. We don't have that luxury on Mars. And further to that, we don't necessarily have to analyze them right away, and we don't necessarily analyze them with destructive techniques. So we can analyze these materials decades into the future where our technology is potentially even better yet. And if you look at the Apollo missions, they returned lunar samples from the moon We recently actually just opened some samples that have been sealed for 50 years since to commemorate the 50th anniversary and utilize some of our technology that is far more capable in the 50 years that have passed since. So with that, I kind of want to wrap with the impact and implications. So I hope I've demonstrated that one, exploring Mars is not an easy feat, but we have discovered a lot of compelling evidence that Mars was once much different than it is today. So Spirit and Opportunity have shown us that water was once much more prevalent on the surface of Mars. Curiosity has informed us that at some point in the history of Mars, Mars could have supported life. And Perseverance is collecting a well-documented cache of samples for eventual return to Earth to assist in us trying to figure out if life ever existed on Mars, in addition to Perseverance itself trying to answer those same questions. And this really, while we're focused on Mars, all these kind of questions and scientific goals loop back to Earth. And here you can see a picture Curiosity took from Gale Crater. If we zoom in, you can see Earth and the moon. And I think it's a pretty good metaphor for what we're doing on Mars. Even though we're exploring Mars, we're very much keeping eyes on Earth, and we're doing it to better understand not only ourselves, but our role and origin in the solar system, ultimately the universe. So Mars could have supported life at a time when nascent life on Earth was just starting to take hold. And when you combine this with the fact that some theorize that the ecological potential of early Mars exceeded that of Earth, and you further add into the fact that Mars likely received a higher flux of carbonaceous debris, craters provided numerous basins of water, the conditions were right, namely wet, dry, and freeze-thaw cycles for the chemical evolution that would be needed to potentially promote life. And also, Mars was not sterilized early in its history. So we have this giant glowing ball in the sky at night, the moon. It formed after a giant impact that would have sterilized Earth, and Mars did not undergo that same process. So this is all kind of pointing towards Mars being a potential place that could have supported life. And if you look at the time periods that we're exploring, so on Earth, earliest life roughly 4 billion years ago, and much of the geologic record from this time frame has been lost. You have crustal recycling, erosion, and we've essentially lost this window into the earliest time that life was taking hold on Earth. On Mars, you don't have that same loss. And we're able to explore these terrains that are, 3 billion years old and have potential windows into this time frame, albeit on a different planet. But we have significant evidence that this planet was once much similar to Earth. So we are really exploring Mars and trying to kind of get a window into this very informative time in Earth and life's history. And we're doing it through the exploration with spacecraft and ultimately leading to bring these materials to Earth, where the technology we have here will really enable us to realize the full potential of our science goals. So with that, just to summarize, the current state of our knowledge is we know Mars could have supported life, but was it ever present? And if life was at one point present on Mars, we have one of two situations. The first, we have at least two origins of life in our solar system. So it's then plausible that, if we have two sources of life just in our very own backyard, it makes sense that it could be quite prevalent elsewhere in the solar system and universe. Or we have life transferring from Earth to Mars or Mars to Earth. And actually, the transfer of material from Mars to Earth is favorable over from Earth to Mars. And if that was the case, if life on Earth started from life on Mars, that would actually make us all descendants of Martians, which I think is pretty cool to think about. So with that, I'll leave with the final point, and that is that in order to realize some answers to these questions and potentially even prompt more provocative questions themselves, terrestrial analyses of return samples from Mars, that is Mars sample return, provides us with the best opportunity to address these questions. So with that, I am going to wrap and leave you with the same way a rover ends every day on the surface of Mars, with a scenic blue sunset. And I am more than happy to take any questions everybody has. Thank you.
Well, thank you very much, Scott, for a very informative talk. And I think one of the things you've shown us a lot of very nice Martian geology and interesting history of Mars, but also touched on some of the technical difficulties and challenges of operating on Mars. And I know that some of the questions in the chat relate to that, and some relate to the geology. But again, thank you for a very nice talk. Let's go to some of the questions. Here's one from John Dwyer. How big does that parachute have to be in Mars' thin atmosphere to slow the descent?
That's a good question, John. I don't have the number off the top of my head. I'm sure I could dig it up online, but you've hit the nail on the head here. So we have a massive spacecraft. So I didn't kind of show a human for scale besides Curiosity or Perseverance. These spacecraft are roughly the size of a king bed in terms of their width and length, and the mast stands 7 feet tall. So they're quite large, they're quite heavy. And then on top of that, the Martian atmosphere is incredibly thin. And when you're entering, you are coming in at a pretty high rate of speed, faster than the speed of sound when you're actually deploying these parachutes. So combined with the heavy spacecraft and the thin atmosphere, the parachute does have to be quite substantial to slow it down. Now, obviously, the parachute can't slow the spacecraft down enough to soft land on the surface, which is why we've had to use inflatable bouncy balls, essentially, in the case of Spirit and Opportunity, but also the sky crane descent maneuver with Curiosity and Perseverance. And yeah, it's not an easy feat landing on the surface of Mars by any stretch. But the good news is we've been developing some technology that has proven to be pretty reliable. And with Perseverance, we've acquired data through cameras that provided us with kind of windows into what it's like to land on Mars for the first time, where we can see the parachute deploy and potentially make iterative changes to the engineering design to best ensure success of future missions, which will have to land with even more pinpoint precision if you're, say, wanting to land a rover beside a cache sample to try and expedite its return to Earth.
I suppose it helps that the gravity on Mars is less than on Earth, but still those have to be big parachutes. Jerome Null asks, were the mountains on Mars formed by erosion or by land movement, earthquakes, etc.?
So if you're talking about Olympus Mons, Olympus Mons is a dormant volcano, part of the Tharsis region. But the mountain inside Gale crater is actually kind of an erosional feature. So you have an impact structure, so a crater, and then depending on the size of the crater and the material that the impactor hit, the kinetics of it can actually result in the forming of a mountain in the middle. And we see that throughout the solar system, on the moon, and there are even some relics of craters here on Earth where we see that as well. But Gale crater is a little bit special because the kinematics of that aren't really conducive to having a central mound that is higher than the crater rim. So there's some other things going on here, as well as some deposition and erosion as well. But yeah, so as far as Gale crater, the mountain in the middle goes, that's just due to the kinematics of impacting sedimentary rock.
Okay, Abhai Vidvans has a good question here about dust. How long is the sun blocked during global dust storms? And are there ideas on how to maintain operation during these periods?
That's a really good question. And to answer the first bit, how long is the sun blocked during dust storms? The answer is too long. But it really varies by storm. So in the case of Opportunity, that storm was one of the largest ever observed, and its central point was right on top of the rover pretty much. So that was a very long duration and very heavy storm. Obviously, if you're on the other side of the planet, it'll be far more punctuated and less extreme. So it really does vary. In the case of Spirit and Opportunity, during these storms, it really becomes kind of power saver mode, where you try and orient yourself as best you can to get whatever solar illumination you can and just use as minimal amount of power as you can to try and make it through. Now, Curiosity and Perseverance, they're not solar powered. They rely on an MMRTG, which is a multi-mission radioisotope thermoelectric generator. Basically uses nuclear heat to generate the heat generated from nuclear decay to generate electricity. So when there are dust storms, Perseverance and Curiosity, really it's just a nuisance in the sense that while it doesn't affect our power per se, it does kind of create the scene around us to be awash with red, and it makes it a little bit more difficult to kind of analyze some materials in pictures.
Okay, here's one from Ken Coppersmith. He says, and this is in response to your comments, I think, about the difficulty of determining scale when you're looking at some of the rover images. Scale, I would think scale could be at least roughly calculated from a number of parameters that the camera or rover could supply.
Yeah, exactly right. And when we open up these images in our rover tools, we can kind of draw lines on there that gives us a ruler and a sense of scale. But if you're looking on the public site, the images are just displayed kind of as downlinked, if you will. So that information isn't as easy to glean. But if you look at an image just without this context of scale, it can be very deceiving as to how big some of the features that we see are. Like I showed a nodule a few slides back, and I continually have to remind myself how big they are because they're smaller than the size of a dime, and we're trying to tease out the composition of them to best inform the composition of fluids that were flowing in the area that formed them.
Okay, let's see. There's one that Patsy Spector asked about at cold temperatures on Mars. How do you provide lubrication for the moving parts? Silicone instead of oils? I pasted in a link to an article that actually details some of the specially formulated grease that's actually used in some of the articulating components. And I mean, you could comment on that if you want, Scott. But one of the things about using grease on Mars is you've got a very low atmospheric pressure, and so it's actually a bit of a vacuum, and the vacuum can actually extract oil from the grease and make it non-functional. So it had to be very specially formulated. If you have any further comment on that, or we could go to the next question.
I think you summarized it fantastically, and I thank you for putting the link in there. I didn't have an answer to this, and the only thing I would add is that the rover does have heaters on many of the actuators, so when the temperature is quite cold, we can still utilize these actuators. But that kind of ties back into when you're operating rover on the surface, many of the constraints that come into play and can limit what you're able to do, again, given how much power you're able to generate or what you have in reserves.
Okay, here's an interesting question. Edmundo Acosta asks, at what point can you detect an object as a Mars meteorite? While it's in orbit? Question mark.
That's a good question. Maybe one you could answer as well. Thankfully, with the Viking mission, we got composition of the atmosphere, and that kind of really informed that some of the materials we already had on Earth were from Mars origin, just due to the composition of the gas bubbles in those stones matching what we'd measured on Mars. But we also have additional techniques here to measure the rocks themselves on Earth, where you can look at isotope ratios, and each of the different, like Mars and Earth, have kind of different fingerprints in that respect. But as far as looking for Martian meteorites from Earth, I think that's a little challenging for a number of reasons. One being just the general size of them. Small objects in orbit can be quite difficult to spot. So I think that would limit it as well. But if Brad, if you have anything to add, please chime in.
Well, Scott, I would give a very simple answer to that question. When it's in the lab.
Okay,
and
good enough.
And that's, to the point of your presentation, one of the reasons we need to get samples back in the lab is that there's so much we can do with them in the lab. As good as the rovers are, and as good as they're the best robotic laboratories in the solar system, but there's only so much they can do, and we can do so much more in labs on Earth. So got to get some samples back.
Yeah.
Here's a question from Ken again, Ken Coppersmith. If there had been life on Mars, wouldn't there be a good chance of seeing some artifact or fissile to prove it? Fossil.
Yeah,
Sorry,
so
fossil.
I
Yeah,
think
that makes more sense. Seeing a fossil to prove it.
yeah, I think the thing to remember here is that when Mars was habitable, the life that was taking hold on Earth was very simple, single cellular, not kind of complex crustaceans and things like that. So this makes it incredibly challenging to find life on Mars because, you know, the evidence of that kind of life on Earth is hard enough to find. And then on Mars, you also have to deal with the challenge of the fact that it does not have a magnetic field. So the surface is soaked with radiation that is particularly not fond of organic molecules, in particular their molecular bonds, and can break these down and make it even more difficult for us to find them. So your question actually points to a very valid reason why we need to get these materials back to Earth, because if there is some lingering fingerprint of biological material there, it is probably outside the scope of what these spacecraft are able to detect. And we really need the best of the best that we have here on Earth to work with high accuracy and try and nail this down. And even then, it's not an easy question to answer.
Okay, here's one that I overlooked. Let's go back to it from Dave Steinberg. He says, what caused the huge change in Mars conditions? Great question.
Yeah, that is exactly what we're doing too. So we're exploring and trying to figure out the evolution of Mars from past to present. And one thing I can say is I just mentioned the lack of a magnetic field on Mars, and this also the magnetic field on Earth also protects us from the solar wind. So you have essentially, you can call it a wind, but it's kind of a flux of particles coming from the sun that hit our magnetic field, and all is fine. But with Mars not having a magnetic field, those particles collide with the molecules that make up the Martian atmosphere, and over time begins to erode the Martian atmosphere. So we know not only from spacecraft on the ground, but also spacecraft in orbit. So MAVEN is an orbiter currently orbiting Mars, and its goal in particular is to characterize the decay of the Martian atmosphere and focus on the Martian atmosphere. And this is in part because we know that Mars once had a thicker atmosphere, the composition was different, and through billions of years and the preferential erosion of certain elements or molecules from the atmosphere would have caused it to lose much of its blanket, if you will, to kind of retain heat and keep the pressure and temperature within the right regime where you would have liquid water on the surface.
Hey, here's a good question. This is Rick Menendez. This is an important question and things we could talk about. Wouldn't the lack of an ozone layer have prevented the formation of life due to the high UV influx? I think you addressed this a little bit, but maybe you want to say some more.
Yeah, I think I touched on that a fair bit. So the radiation on the surface now is definitely problematic. However, there are some potential environments that life would have had some protection from radiation, namely kind of near subsurface type of environments, which is part of why we're drilling cores and things like that as well. But yeah, there's, as much as there are things going for Mars in terms of potentially of supporting life in the past, there are also many things working against it. And it really, you know, I mentioned that we're keeping eyes on Earth. It also should cause us to have pause and appreciate the wonderful little lifeboat in space that we're on, and how precious it is.
Okay, here's another question. Is it possible to make a cable elevator from a satellite to the surface? Atmospheric conditions, cost, is it even possible?
Yeah, so this is a space elevator type question, and I know they're pretty popular in science fiction and even some studies and engineering tests, kind of theoretical in nature, being done now. The thing that you kind of have to remember is that there would really, again, feel free to cut in here, Brad, but in my opinion, they'd really only be feasible from like the surface to a geostationary or Martian stationary orbit, if you will, just due to the mechanics of it. But I think technologically they require kind of the carbon nanotube structure that we don't quite have yet. And as far as a practicality and cost standpoint, I don't see them being utilized in our lifetimes.
Yeah, I agree. Way in the future, perhaps. Here's one from Edward. Does Mars still have a molten core? Could its volcanoes become active again?
So the answer to that is no. So there's this is part of why there's no magnetic field. So we have our active core to thank for our protective magnetic field on Earth. And when that was lost on Mars, you know, all the volcanic activity went with it, as well as any kind of magnetic field as well.
Yeah, I think you may have just addressed this about the dead or dying Mars magnetic field. Do we know how it's evolving today? The stratification of mountain deposits could perhaps tell us more. I remember hearing that some magnetic field still remains. That's from Liliana.
Yeah, I'm not that familiar. To the best of my knowledge, if there is something that remains, it's incredibly weak and not really sufficient enough to kind of be indicative of an active core or some kind of protection from solar wind. Brad, do you have anything to add to that?
No, I think that's right. I mean, we can measure it today, and what remains, there's a remnant magnetic field, but that's locked up in the rocks, and so it's not that there's no active core dynamo now. Okay. So let's move on to maybe perhaps one more, and then we can call it a morning. From Emmanuel. In addition to liquid water, were the remaining conditions in young Mars, concentration of necessary compounds, temperature, etc., able to potentially support life?
That's a very good question as well. And the one thing I want to point out is part of the answers in the question as well. So the fact that there was liquid water suggests that the temperature was favorable to life as well. But as far as concentration of necessary compounds, I'll just flick back a couple slides here. Just here. So part of what we've done with these spacecraft is we've thoroughly characterized the composition of many Martian materials. And several of the bioessential elements that are required for life to have a fighting chance, we found in varying but not insignificant abundance within these materials. And there's actually a paper out by a colleague of mine recently in the journal Life by Ben Clark, and he goes into great detail into essentially this exact question as to why Mars may have been kind of a happy home where life could have had a fighting chance.
All right, let me just ask if I missed anybody's question, feel free to unmute yourself and ask it at this point, and we'll wait just a second or two and see if there are any residual questions.
I just placed one, but
go ahead.
There was like, are we planning to, if we ever go there, are we planning to extract water from the rocks? Are we going to, you know, expect to find water somewhere in the poles, or what are we planning to do?
Yeah, that's another good question. So ISRU, in situ resource utilization. As far as sending humans to Mars, one of the main challenges, one of many significant challenges, is to get them back, right? And anything you bring there requires more fuel, adding more fuel requires more fuel, and it just becomes a snowball problem. So if you're able to utilize the resources on the surface of Mars to assist, this significantly reduces the kind of cost of the mission. So water is definitely one way that we can mitigate some of these challenges. We know there's plenty of water, even just in the soils, that is abundant throughout the planet. But also Perseverance has an instrument called MOXIE, and it doesn't use water per se, but the whole premise of the instrument, and there have been several tests of this instrument, is to take carbon dioxide from the atmosphere and convert it into oxygen, which can be used as propellant. So your question pertaining to extracting water, I presume in the case of ISRU is definitely something very much on the forefront, and is definitely on the forefront of the Artemis program and the potential long-term habitat somewhere on the moon where there is water ice present, particularly in the permanent shadows of polar craters.
Thank you.
I've got a question.
Sure.
What about, I mentioned about the fact we have a large moon, it stabilizes our axial tilt. The lack of larger moons on Mars, would that cause wild climatic swings and make it hard for life to evolve?
Yeah, so our moon also benefits us, as you mentioned, by stabilizing the variation in Earth's tilt. Mars does not have that luxury. It does have 2 small moons, and actually evidence suggests that these moons are kind of they accreted from debris kind of similar to Saturn, and then eventually will kind of be crushed by gravity as their orbits decay, and then process repeats. But yeah, this is something as well. The tilt of Mars's axis has varied, and that does add complications for long-term stability of life. But given what we know about the Martian history, we suspect that the presence of water and therefore the potential habitability could have been localized and punctuated. So I'm not sure if the timescales will really conflict.
One more thing, you said the moons aren't captured asteroids. I thought they were captured asteroids.
So that was a theory, but there have been a few papers that have come out with simulations that have shown that, in particular, the decay would cause the one of the moons to essentially break up as it began to experience tidal forcing in excess of the binding of the material in the moon, and this would form a ring, and then over time that ring reaccretes into a moon. And actually their simulations predicted kind of precisely the orbits of Phobos and Deimos right now. So I shouldn't say that it is a settled debate. It is still very much debate, but there have been a couple very insightful papers that have suggested that capture asteroid is less mechanically favorable than the accretion and tidal fracturing of these bodies.
Where did the initial material come from?
That's a good question. I'm not sure. It could have been a captured asteroid that has then been fractured and reaccreted into multiple. But as far as Phobos and Deimos both being captured asteroids, these papers have kind of casted a little bit of doubt onto that in particular.
That's new to me. Thanks.
No problem.
It's good that we have some things still to figure out.
There's plenty. Brad, whenever we learn something, I feel like we have multiple more questions ahead of us. So there's no shortage of work to do.
Well, let's bring the questioning to a close and thank Scott once again for a very interesting and insightful lecture. And he's leaving us with one of the most spectacular kinds of images you could imagine from another planet. And gosh, Mars sure is Earth-like in many ways. Let me just remind you that next Saturday will be the final in our series of space science related lectures. It'll be given by Professor Paul Byrne, and he's going to be talking about the forgotten planet, Venus. Or is it the forgotten planet? So tune in next week. Paul's a very engaging speaker, and I think you'll enjoy hearing what he has to say. So thank you all very much for joining us this morning. It's been a fantastic lecture. Thank you again, Scott. And I'll put up my reaction there and then say, everybody have a great Saturday, have a great weekend, and we'll see you back here next week.
Thanks all. Stay warm.
Thank you all.
Thank you. Excellent.